about 10 seconds of footage that is so trippy. Hello, and welcome back to my channel. I've been away. This is the first time I've actually tried to record a proper video for 2 months. Is that right? 9th of May? Yeah, sometime in March. Yeah. So I hope you've been well. I've got a lot to talk about, but something happened this week which I thought might make a cool topic for a video. I was teaching a student the other day, and I wanted to tell them a little bit about Fermat and his famous last theorem. And I discovered that this book exists. Have a look at this, it's pretty crazy. It looks like it's 1670. Okay, it's a first edition. It's an edition of Diophantus Arithmetica, but it has Fermat's annotations in it. And I had been wondering why I couldn't find a copy of Arithmetica on Amazon. This is on SophiaRareBooks.com. The price for this book is 50,000. But so what's all the fuss about? Diophantus. Let's talk a little bit about Diophantus. Born sometime AD 201 and AD 215. Died around 84 years old. It's probably sometime between 285 and 299. And he was an Alexandrian Hellenistic mathematician who was the author of a series of books called Arithmetica. So what happened was Pierre de Fermat used to jot down notes in his copy of the 1621 Diophantus Arithmetica. So enough of the history. What I really want to show you, this is the little nugget that I found that I thought was pretty cool. Here it is. The most famous marginal note is, of course, that which accompanies Diophantus Proposition 2.8, which is on page 61 of the edition that Fermat was reading. To divide a given square number into two squares. But I might as well go on now while we're here and just mention that Fermat adds, in contrast, it is impossible to divide a cube into two cubes, or a fourth power into two fourth powers, or in general any power beyond the square into powers of the same degree. Of this I have discovered a very wonderful demonstration. This margin is too narrow to contain it. That paragraph, that note in the margin, started a 300-year problem, battle, story, thing. So it says here, over the next 2 centuries, 1637 to 1839, the conjecture was proved only for the primes 3, 5 and 7. Although Sophie Germain devised an approach that was relevant to an entire class of primes and so on. And it wasn't until an Oxford mathematician, Professor Andrew Wiles, solved the problem around 94-95, and he proved it for sure. What we should be able to do here is experiment with the actual problem, or the formula which Diophantus threw out there, which prompted Fermat to discuss this in the first place. I cannot do this. Oh, okay, I got it. So let's see what this actually means. Say we use a equals 1 and m equals 1. Why not? Nice simple one. So on the left hand side of this equation we have 1 times, that's a terrible bracket, 1 squared plus 1, close brackets, square the whole thing. Ooh. Squared equals, right, now this is easy, what's a times m? 2 times a times m is 2. Ooh. 2 squared plus 1 times 1 squared minus 1. That's 0 squared. Guess what? This one is not good. This one is going to say this is 2. Times it by 1. 2 squared equals 2 squared plus 0 squared. Okay? It's true. Let's stick with a equals 1. And now let's use m equals 2. Okay, 1 times 4 squared. No, 2 squared. Plus 1. All squared. Equals 2am. 2 times 1, or 2 times 1 times 2, 4 squared. Oh, this is going to be a good one. This is going to be a good one. Okay. Plus 1 times 4 minus 1, all squared. Bear in mind that Diophantus came up with this about 1800 years ago. Okay, so what have we got on the left? 2 squared plus 1, that's 4 plus 1. 5 squared equals 4 squared plus. Now we could do this 2 ways. We can evaluate this, or we can say, well, we know this is 25 and we know this is 16, so guess what, this ends up being 9, because 16 plus 9 is 25. But let's have a look at what's in here. 4 minus 1 is 3. There we go. So we get 5 squared equals 4 squared plus 3 squared, which is true. And actually, if I scrub all this as well, this is a good time to mention. So we just had this 3 squared plus 4 squared equals 5 squared. So the question is, can you think of 2 ways to visualize this? And the first way, now I don't really know how to use this package here. What is this? Paint 3D. So let's do, you must be able to do lines. Let's do, no, 2D shapes. 2D shapes, oh excellent, right angled triangle. Hello? What's this? Me wanting to have a black background has caused a bit of a problem here, hasn't it? So what happens if we go, let's experiment. White, fill it white. Now go to shapes, right angle triangle. Yes, it's a black triangle. If the base of the triangle is 3, put a little right angle here, and the height of the triangle is 4, then the hypotenuse will be 5. So these little groups of 3 integers where you can write things like this. They're called Pythagorean triples, and there's an infinite number of them. Okay, so we have a wobbly looking square, a not very square square, but hopefully you can see it's 5, 5, 5, 5, 5. It's 25. If I select, I can take this and I can cut it and then paste it over here. Wobbly. Alright, let's fill in. Let's fill this thing in. Right. Horrible wobbly squares. But yeah, we have this square plus, so this square here is 16, this square here is 9, and we've already seen that you can add the two together and get 25, which is also a square. So yeah, I'm going to try and go through this whole thing without writing down the dreaded Fermat equation, which has become the sort of standard way of communicating this. You know, instead, I think it's great to think about this Diophantus method of breaking squares into smaller squares. And then it's quite simple to say that if you think of a cube, imagine a Rubik's cube, and my Rubik's cube is 3 by 3. So this Rubik's cube is 3 by 3. Okay, and you can, oh god, I keep saying okay because I haven't made videos for ages. I've suddenly got a video tick. We have a nice solid cube that looks better than my drawings of squares, and I'm hoping you can see kind of in the front of this there is a smaller cube, which is here. There's a 2 by 2 by 2 cube. If I could highlight that in a different colour, that would be really cool. Note to editing me, don't even bother trying to do that. So what Fermat was saying about this cube, and all cubes in fact, is if you take that, if you break this, if you break that 4 cube out, which is, what is that? How many pieces are in that? Oh, it's 2 by 2 by 2, isn't it? It's an 8. It's a cube of 8 pieces. Okay, if you take those 8 pieces out, the remaining pieces cannot be arranged as a cube, and that's true for all cubes. But there's something, if you want to find out more about any of this kind of stuff, 2 channels I'd love to recommend. 3 blue, 1 brown. Actually 3 channels, 3 blue, 1 brown, Numberphile and Mathologer. Now Mathologer did a video where, I hope I've remembered this right, what he was saying was that you can break a cube into 3 cubes. I'm not saying every cube, because just like the squares, we found that there was a square, the 4 square couldn't be broken into 2 squares. I'm sure there are cubes that are the same, but it is possible to make a cube from 3 cubes. And also if you continue going up through the dimensions, so if you had one of these in 4 dimensions, if you can imagine that, roughly, so this, notice how this cube, for each dimension, each of the 3 dimensions, it's got 2 faces. So my guess about a 4-dimensional cube is it'll have 2 faces on the ends of each dimension. So instead of having 6 faces, it should have, I think it'll probably have 8 faces. But if you could imagine that cube, you can't break it into 2, we'll call it a 4 cube. You can't break it into 2 4 cubes. I don't think you can break it into 3 4 cubes, but you can break some 4 cubes into 4 cubes. So there you go. I just wanted to show you that nice method that Diophantus had written in his book that prompted the 300-year struggle to solve Fermat's last theorem. And I just want to say hi to the 5 people who watch my videos. I feel like I know you all personally. Thanks ever so much for watching and commenting. And if you're new here, please like, subscribe, ding the bell and comment below. Thanks a lot. Bye.